All right, we're going to go ahead and get started here. Welcome to our webinar. This is Modeling and Automating Human Preferences for LLM Evaluation. My name is Skip Everling. I'm heading up Developer Relations here at Kolena, and I'm going to be joined by Gordon Hart, our CPO and co-founder. The topic today is really about LLM evaluation, of course. We're going to talk about the challenge of evaluating LLMs efficiently and consistently, and the best ways to do it. We're going to talk about a new technique that will leverage human evaluation, which is highly valuable but time-consuming, can be inconsistent, and difficult to scale. So we're going to talk about what it's like to model those human preferences, and then therefore be able to start to automate on top of that. Gordon's got a lot of cool stuff he's going to show us. Yeah, looking forward to this webinar. Before we get too much farther, just wanted to say a quick word about Kolena. Kolena, we're the AI quality company. We hosted our first big conference over the summer, AIQCon here in San Francisco. It was a great time. We had 20,000 plus attendees in total, all kinds of great technology partners, regulatory partners. I mention this because we now have the talks up on YouTube. They're still getting posted, but many of them are already up there. If you just look up AIQCon or Kolena, the talks there will come up. There's a lot of good quality talks on topics related to evaluation, LLMs, all kinds of stuff. So I encourage you to check that out. Also, we'll be probably running this again next year, so keep an eye out for that. Well, the agenda today, I'll turn my video on. The agenda for us today, we're talking about the landscape, just a quick overview, the landscape of LLM evaluation. I won't go too much into this, but we're going to set the stage here for why the technique that we're going to show you is so valuable. So particularly the critical role of human evaluation. Then we're going to get into head-to-head evaluation and model ranking leaderboards. You've probably seen these out on the internet, and they can be really powerful directional signal that we can actually leverage. Talk about fine-tuning using that information, and then getting into modeling human preferences, automating these contests, ensembling models and judges. And then Gordon's going to give us a very cool demo of what we're calling auto stack, putting it all together to build better Gen AI products faster. All right. So just a quick introduction here about the LLM eval landscape. Some of you may already be very familiar with this. Some of you may be a little bit newer. So I just wanted to give a little introduction here. Basically, there's a lot of promise and challenge in effective LLM evaluation. These LLM evaluation frameworks, though, in general, are really crucial for ensuring reliability, safety, and performance if you intend on deploying an LLM model and having end users use them. First, most obvious thing, quality assurance. You want to make sure that what your LLM is producing is accurate, it's relevant, it's coherent, it's doing it well across diverse scenarios. You want to have a high quality product, and you need a way to evaluate that, test that. Safety and ethics, extremely important. Identifying potential harmful biased responses, mitigating responses associated with AI deployment. Also things like regulatory compliance, so being able to demonstrate that you have a safe product and that your LLM is incorporating all of the regulatory constraints appropriately. Performance optimization, of course. So being able to target improvements to your model is something that you can do much better if you have an evaluation framework and you're being intentional about what you're testing and how you're testing and how you're getting feedback. The challenge across all of this is that you have to balance the costs of time and effort testing against the quality standards that you have for your product. There's no fixed goal that you get to where you have 100% good product. It's always a matter of reaching a target, a gold standard target, and doing it as efficiently as possible. It takes time and effort, especially for things like human evaluation, because it's not cheap or easy to get a good, reliable large set of human raters. So that's the challenge in general with testing. It's extremely important, but it does have some costs associated with it. So some of the standard tools and techniques that are out there, the most automatic one that you can use right now is basically these computed metrics. So these are examples of some metrics that can be computed for text tasks in general. Things like assessing the similarity or the expected result of a text generation process based on what you're expecting to see. These are great because they're easy to compute. They provide quick feedback. You can get feedback right away. You can take a look at those and compare them all. But the problem with the computed metrics alone is that they fail to capture some of the nuanced aspects of things like language quality, coherence, context appropriateness, things that a human would be able to detect in a way that is maybe not explicit enough or quantitative enough for an automated computed metric to capture. So that's the downside with these. Another tool is these benchmark data sets. You've probably seen these. They're often coming out in specific domains. So things testing like math or reasoning capabilities, or in our last webinar, we looked at a finance benchmark data set. So specifically, question answering for a financial document data set. And these are great because they give you a sense for comparing models on the high-level domain tasks that are relevant to whatever your model is going to be in. So being able to get a high-level sense for how well your models are performing in those areas. But the problem with a benchmark data set is that it's hard to know how well these kind of standardized tests translate to real-world use cases. It's the same thing for a standardized test in school versus working in the real world. It's not exactly the same thing. So you can't just use a benchmark data set and be done with it. And these also get gamed and become stale as they're public. And so models start to get developed against them and start to optimize for them. And they don't necessarily reflect what it would be like if you adopted those models for your own real world use case. And then of course, human evaluation. So this is where human raters will subjectively assess LLM outputs based on criteria like fluency, relevance, and factual accuracy. This is really the gold standard for quality because human judgment is what matters in the end. You're going to have humans consuming the outputs of these LLMs. Human judgment is really the best signal for many of these factors that you will want to have. And so this is really a gold standard for quality in terms of evaluating LLMs. The main problem with human eval is that it can be really time consuming and expensive to collect the data. And it gets difficult to scale for those reasons and for other reasons as the required volume increases. So I want to dig into this a little bit more because this is the gold standard. I'm trying to think about, okay, how can we capture more? How can we do more of this gold standard as opposed to just relying on some of the other things because we can't afford the costs of human eval? So we're going to focus just a little bit on human eval for a moment. Just the process here for collecting human evaluations, just to give you a sense for what it's like. You'll design an evaluation task saying you want the humans to decide how coherent a response is between two outputs, between two LLM outputs. You then set up, you generate results from your LLMs based on some prompts that you've set up for the task. You then have to recruit raters, and this is a big important step. It sounds very simple, but you need to make sure that you are getting a diverse set of raters, for example. You have to think about what bias is being introduced. You have to make sure that you have enough, a large enough set to be meaningful. There's a lot going on here, and there's a whole part of the industry that's focused on this, but that's a very key part as well. And then you get into the evaluation process. So you would establish a criteria such as a Likert scale, meaning like a 1 to 7 scale, for example, would be a Likert scale, or a head-to-head comparison. Is this better or is that better? You have to have a rating interface, so someplace where the raters will go in and actually say, this is better or that is better. You collect those human judgments, and then you deal with the data. So you're going to aggregate and analyze the results. And then ultimately, you're going to use that collected data to fine-tune your models. And that's going to make, if you've done all the previous steps right, that's going to be a big value add for the quality of your model. This is just a quick example of what a head-to-head evaluation is. You may have seen something like this before. A head-to-head contest just presents raters with 2 different model outputs generated from the same input, and it asks them to choose what's better. In this case, we're looking at an image generation task, so it's not an LLM per se, but we ask these 2 models to generate a snowy owl standing in a grassy field. Got Model A's response, Model B's response, and the human rater will say, okay, for style, which one was better? Model A, neither, or Model B? How well did they follow the prompt? Model A, neither model, Model B, etc. This is an example of an individual rating system that you might collect in a head-to-head way. So kind of to recap here, human evaluation. So human raters, they subjectively assess LLM outputs based on a lot of this subtle criteria. It captures preferences on nuanced aspects that otherwise wouldn't be captured by automated metrics. It's really the gold standard in terms of quality, but it's got several limitations: time-consuming and expensive. There's bias in raters. You have to mind the diversity of your annotators. It's difficult to scale. So how can we get past these limitations? How can we use this more? The idea we're going to present to you today is modeling these human preferences and automating these head-to-head contests so you can really accelerate the process without necessarily needing to have a larger set of human evaluators. So we've got Gordon here to talk about this with us today. Gordon is our Chief Product Officer, one of the co-founders of Kolena. He's been a software engineer and product manager in real-world AI initiatives since 2016. He's built some cool CV/ML systems for defense and security. You can see him here at Tokyo Narita with a threat detection system. And he spent the past several years thinking very heavily about ML quality, AI ML quality here, data modalities, task types, etc. Very excited to have him with us here. I'm going to go ahead and hand it over to Gordon now.
Thank you, Skip. All right. So I'm going to talk through the process of what it means to model human preferences and how you can use this to effectively test systems that you're building with LLMs. So if you've been in the space building for a while, you've probably seen a bajillion tables that look like this. Almost every newly released model has one of these where it shows a bunch of different benchmark data sets like GPQA, MMLU, GSM-8K. There's maybe a dozen or so really common ones that show up in all these data sets in all of these different model cards. And every time a new model is released, it gives their performance across these data sets and compares it to previous models. You can see this one is particularly from the Claude 3.5 Sonnet release, but this table is very familiar. This is from Llama 3.1 release. This is from the Gemini 1.5 paper. This is from the Gemma 2 release. They're everywhere. Every time that you see a model released, you get something like this that supposedly at least tells you how it performs. If you've also been paying attention and following along in the space for a while, you've probably realized that those benchmarks leave a lot to be desired when it comes to telling you how the model is actually going to perform in the real world. And you probably trust this, which is the LMSys Chatbot Arena leaderboard, to give you a more concrete signal about which model is going to perform the best when it actually has to interface with humans. So in this Chatbot Arena leaderboard, rather than having a fixed benchmark data set, you go and input a prompt and you see responses from two models side by side. And you as a human get to vote on which one you think is better or if neither are better. That many of these head-to-head comparisons contribute to an overall score for that model. And you see all of these models ranked based on the head-to-head battles that users have voted on, which one they think is better in this kind of unbounded form factor. So this gives a much better signal in terms of how humans perceive this new model, whether or not it's better than previous ones, much better than, let's say, MMLU performance going from 82% up to 84%. It's very hard to know if that means your model is actually going to be better when it comes to real ambiguous tasks. So this head-to-head comparison that is reflected in the LMSys is very necessary for tasks that have a lot of nuance to them, where the correct answer is either difficult or impossible to judge. As an example of that here, this is a prompt where user says, write me a haiku. And let's say we're making a haiku writing system. This is a little toy example, but many fit into this box. If you have a single response from a model, which is a generated haiku, it's almost impossible to say, is this haiku good? You can do things like, does it follow the rules of a haiku? But that doesn't actually tell you how good it is. But if you were to view two side by side, as a human, you can decide which one of those is better. And as you collect many of those ratings, you get a pretty strong signal about which actually does a better job of writing haikus that humans like. So trying to assess one of these model responses in isolation like let's say trying to come up with a haiku goodness metric, like Skip was talking about. Maybe you have a model that's ranking haikus on a Likert scale between 1 to 7. That's a fool's errand. You're never going to get a metric that is reflecting the way that humans perceive these haikus. The way that you would get a ranking when you have a human viewing these side by side and allowing them to pick which one they like better. If I was asked right now, which one of these, on 1 to 7, how good is this haiku? I would have an extremely hard time judging that. But if I'm able to pick between these, I can use my discretion here and say, I think response A's haiku is actually better. This GPT-4 haiku is a little better than this Mistral large haiku. This kind of nuanced task is everywhere with Gen AI. This is why we like Gen AI. This is why it's the thing that everybody's talking about now, because unlike predictive AI, you can throw it at all sorts of ambiguous tasks that have unstructured inputs and unstructured outputs, interface with real humans, and you don't need to come up with some sort of rigid definition of what your product is, what good is and what bad is, the way that you previously needed to with predictive AI. So this head-to-head comparison process is something that you can run many times to get you can run many times with one model and another model, and you can turn those into a leaderboard that ranks many models or maybe many versions of your RAG system, many different prompts that you're trying out. And you can turn those head-to-head ratings into an overall score with the ELO rating system. If you played chess, you're probably familiar with this, or lots of other games. The ELO rating system is used in environments where there's many one-to-one competitions between participants, and whoever wins a given head-to-head gets an increase in their score, and whoever loses gets a decrease in their score, proportionate to the strength of the opponent that they're facing. In cases where a tie is possible, like in which model is better, maybe neither is good or both are good, would be considered a tie. And this increases the lesser player's score by a little bit and decreases the better player's score by a little bit. You can also, in the ELO rating system, calculate confidence intervals, which are very useful to mitigate any noisy rating signal. If you have many human raters, you're probably not going to get the same answer from all of them. But if you have enough ratings, then you can get a pretty good idea by computing confidence intervals, where you recalculate these scores by running all of those head-to-heads in a different order to get a general idea of what the upper bound and lower bound for that ELO score would be. And then you can compare confidence intervals between models rather than just the score taken in isolation. And this is really helpful if you have noisy rating signal, maybe coming from unreliable humans or coming from an automated judge, which we'll talk about next. So this head-to-head voting process is inherently very manual in the way that it's set up with LMSys. It requires the LMSys leaderboard, requires a ton of human labor to compute. And because it's crowdsourced, a bunch of people are happy to provide that labor. But this is not necessarily feasible for businesses. And so if you wanted to recreate a leaderboard like that with human ratings, you would need a large pool of labelers, of raters, who would be constantly reviewing results from your new model and comparing it against maybe a previous model and deciding which one they liked better. And this is maybe feasible in small batches, maybe right before you're going to make a new big release, but it's not feasible for the regular development process where you're making changes constantly. You want to tweak this prompt, you want to tweak the way that you're retrieving context from your RAG system. You can't really run that large-scale human evaluation for every single one of those changes. So one way that you can automate this is with what we call a judge model. This is using an LLM to provide that preference rating where it decides which one is better, A or B or neither. And judge models are surprisingly effective at reflecting human preferences. This is an example here where the yellow line is the actual ratings of some models on the LMSys leaderboard, and the blue line is the predicted rating, which is predicted using a judge model that has only 65% accuracy, meaning 35% of the time it disagrees with whatever the human was saying, but still reproduces the actual rank with a pretty high degree of fidelity. On average, these are the ranks that are predicted by the model in this experiment that we ran using the LMSys chatbot arena dataset. On average, they're less than 5 places away from their real rank, and the top three models are all in the top three, and all of the bad models are pushed towards the end. So this is a highly effective process that you can make even better with something that we call a jury. This was introduced by Cohere in a paper from earlier this year in May, where they named it poll. The idea in the poll process or the jury process is that rather than using one judge model, you use multiple judge models that are coming from different developers, coming from different model families. They have different training methodologies, they have different training data sets, and so they will have likely different views. They have different alignment processes that have been run. And if you use multiple of these models in a jury, you'll get you'll get judgments that are better than you would get from a single large model like GPT-4o. So an example of what might be within a jury here is, let's say Cohere's command R is 16 times cheaper than command R plus. GPT-4o mini is 30 times cheaper than GPT-4o. Claude 3 Haiku is 12 times cheaper than Sonnet and 60 times cheaper than Opus. And all of these models are also faster to run. And together, a jury of these three cheaper models, Command R, GPT-4o Mini, and Claude 3 Haiku, is more accurate than any frontier model like GPT-4o Full, and will also run much faster and be much, much cheaper for you in the long run. Because these models, even if you're using 3 or 5 of them, this jury is a fraction of the cost of running just one frontier model. The final process that we can use to improve this head-to-head voting process is by fine-tuning a preference model on our own human votes. For many tasks, it's challenging for a off-the-shelf model to judge how users would vote. But with a little bit of data, we can fine-tune a base model to model the way that a human would have voted. A is better, B is better, neither is better. We can fine-tune a model to predict that with much higher fidelity than you would get from even using a jury of many models. So this fine-tuning process can be a really small model, like 2 billion parameters, 9 billion parameters. These are models that you can run on your laptop CPU very quickly and will be much better at judging, at deciding which the way that a human would have voted than a frontier model or a jury of smaller models. In this example here, we've fine-tuned a 2 billion parameter Gemma 2 model. This is a very small model. It's very fast to run. We fine-tuned that on the Anthropic helpfulness harmlessness data set, where we're trying to predict harmfulness of a LLM response. This is a very hard task. It's got a lot of ambiguity. What does harmfulness mean? And a fine-tuned Gemma 2 on this data set, you can see here, we have a comparison versus GPT-4o, GPT-4o Mini, and Gemma 2 2B. This fine-tuned model is the most accurate. It's 10% more accurate than GPT-4o Mini and 8% more accurate than GPT-4o. It's the fastest to run by far. This is a model that you can run on CPU. This is a model that, if you run on a GPU, will be blazing fast for this prediction task. And it is the cheapest to run as well. Even on a GPU machine, this is much cheaper to run than GPT-4o. This 3.66 is on a log scale, so GPT-4o is way, way more expensive. And it's a little bit cheaper than GPT-4o Mini as well. So the question then is, how difficult really is it to fine-tune a judge model? And it depends on the complexity of your task. For simple tasks, you can fine-tune a judge model to a really high degree of accuracy with just tens or hundreds of examples. And this training time, you only need to run through, let's say, about 3 epochs. This training time will be minutes. For a task of middling complexity, you might need hundreds or low number of thousands of examples to fine-tune it. An example here is a way that a human would have voted. So given a prompt and responses from 2 models, which one would the human have preferred or neither? And this medium complexity might take an hour or 2 to fine tune. And for a very complex problem like this helpfulness or harmfulness prediction, requires somewhere in the thousands to tens of thousands of examples. This helpfulness harmlessness data set that was provided by Anthropic has about 40,000 examples, and the training time is about 12 to 24 hours on a single GPU. And the secret here is, you probably heard this term before, it's using a LoRa or a low rank adapter to train a tiny percentage, let's say 1% of the overall model weights, rather than fine tuning the whole 2 billion parameters or 9 billion parameters. You might just be fine tuning a couple million. This LoRa process is highly effective. It makes this training process, because there are so few trainable parameters, this makes it very data efficient. You can use hundreds of examples and get a great fine-tuned result with this LoRa approach. It's time efficient. You can run this on a single GPU and train something in somewhere between minutes and a day. And it's very compute efficient. These numbers, these training time numbers, are quoted not with a crazy cluster of GPUs. This is a single NVIDIA 3090 GPU that can perform this training process very quickly in real time, not something that's more similar to the way that these LLMs are trained on a crazy amount of hardware, but something that's more similar to how predictive models are trained. These are training times that we're all familiar with as machine learning engineers. This is what machine learning kind of looked like before the advent of really large models. So with that framing, I want to jump into this application called AutoStack. And let me end here. So AutoStack is an app that we've developed at Kolena to facilitate this head-to-head comparison between a bunch of models. We're here on AutoStack looking at this LLMsys chatbot arena dataset. This is a dataset that was released on Kaggle that has about 40,000 head-to-head matchups that came from the LLMsys arena, as well as the way that the human on the LLMsys arena actually voted. So using that data, we can seed this leaderboard here and compute ELO scores and confidence intervals to show us how the 64 models in this data set stack up against one another. These models have somewhere between a couple hundred to a couple thousand data points, and there are a similar number of votes for each model. And so we can see here that our champion model is this latest GPT-4 preview from this data set. And we can click in here to see the history of how that ELO score evolved as the number of votes increased. And we can see the head-to-heads against other models that have also, that are included on this data set, other models that shared the same prompts that had human rating A or B. So all of these judgments came from humans. We're using this chatbot arena data set, which is all human judgments. But since that's not often available to us, AutoStack is built to allow you to run a judge model or a jury of models to perform this rating process automatically. If I jump over to this judges task, I can go ahead and configure that jury that we talked about earlier. I can go ahead and add a Cohere Command R model and go and create that. I can go ahead and add the OpenAI GPT-4o mini model to use as a judge, go ahead and create that. And I can go ahead and finish this jury out by adding the Claude Haiku model. And you can see here, this is a very simple system prompt. These judge models, we're just prompting with the system prompt, providing them the user's prompt and then the responses from two models, and having this judge model decide if A or B or neither is better. Go ahead and create that. So now that we have these three judge models configured in this jury, we can come to the leaderboard and see how a new model would stack up against these. This LLMsys chatbot arena dataset came out before GPT-4o mini. And so we can see, if we want to learn how GPT-4o mini would stack up on this dataset, we can go ahead and upload some responses from GPT-4o mini by selecting a CSV file here. This is a CSV file that just contains the prompt and response columns. I actually have this open here. This is what this file looks like. It's just prompt, explain function calling. How would you call a function? And it has the response from the model. And when we upload this to AutoStack, this will automatically match it up against models that have run on those same prompts and do that judging process with all of those judges that we've configured on our jury. So now that we've added this model, we can come to our tasks drawer and see that we have an automated head-to-head judging task in process where we're using this jury. We're using Claude 3 Haiku, GPT-4o mini, and Command R to process each of the matchups in the model results that we've just uploaded with models that are already existing in this LLMsys chatbot arena AutoStack project. And we can come down here and see we have GPT-4o mini. It has no votes yet, so it has the default ELO score with no confidence attached to it. And once we've completed this judging task, we'll see it here. We'll see its ELO score history over time, and we'll see how it fared head-to-head against other models. While we're waiting on this, we can go and jump into see what we uploaded from GPT-4o mini. And so we can see here, these are the prompts and responses that we were looking at in that CSV earlier. Explain function calling, how would you call a function? And we have the response from the model. We can click through and see other responses. What is the best way to travel from Tel Aviv to Jerusalem? Give an example here. And if we want to provide human ratings, if we don't want to use automated judgments, but we want to actually judge this manually, we can go ahead and select another model to compare it against. So any of these other models that have been uploaded, we could select. I'm going to go ahead and select a random model. And this is now GPT-4o mini versus Claude 2.1. And we're showing the 3 head-to-heads where these models have results from the same prompt. So write a Python code that calculates sum of 5 and 10. And here's the response from GPT-4o mini, and here's the response from Claude 2.1. And we can use this interface or the hotkeys to provide our human ratings of which we think is better. So let's check on the progress of this task over here. We're almost through to the final examples. So now that we've completed judging for all of those examples that matched up with other models, using all of the judges that we've configured in our jury, we're now recomputing the leaderboard, and we've now completed this task. So we can come back to this leaderboard and see that this GPT-4o mini model ended up 4th on the leaderboard, which is maybe to be expected. It's better than a lot of models. If you use mini, you realize that it's a very, very good model, but it's falling a little bit short of these full-scale GPT-4 models, particularly the newer revisions. So we can now click in here and see, here's how this model's ELO score changed over time. We can see the votes from the different judges here. Here's how Command R voted. It generally favored this GPT-4o mini model. Here's how the GPT-4o mini judge voted. Maybe it shouldn't be voting on itself. And it also favored the GPT-4o mini. And here's how the Claude Haiku voted, which had a lot of votes in favor, but also had a lot of votes against it. And so the score decreased a little bit from the Claude 3 Haiku model in this jury. So we can see here, let's look at the judge model Claude 3 Haiku versus all of the different opponent models. And we can see the record that this model had, that our GPT-4o mini model had against all of the other models that it was matched up against. And so in this case, against Starling LM7B Alpha, Claude thought that it lost all 3 of these battles. I want to say again, right now we're looking at different models like GPT-4o mini or GPT-4, but this can be used for fine-tuning your prompts, for example. If you want to be doing prompt engineering and changing prompts, that will produce different responses. And so you can rank the same model with just different prompts against each other using this same process. If you are using a RAG system, if you're changing maybe the way that you're turning your data into text, if you're changing the way that you're chunking and putting things into your knowledge base, if you're changing the way that you're retrieving data from your knowledge base, or changing your re-ranker, if you have one of those plugged in, responses from different versions of that RAG system can be uploaded here. And you can have your judge or jury go and decide which of those systems produce better results. We can click one of these records now to jump into the head-to-heads. So we see now GPT-4o mini versus this Starling model. And if we want to see our judging history, we can go and click here. And we can see now that both GPT-4o mini and Command R preferred this left model, but Claude Haiku preferred this right model. And we can click through here and see places where these models agreed and places where these models disagreed in their judgment of which one of these was better. In this interface as well, if we want to provide our own ratings, like let's say I thought GPT-4o mini was better in all of these, I'm just going to go ahead and click left. I'm going to compare it to a different model. Let's say we thought GPT was better in all of these. Go ahead and compare it to a different model. We'll say GPT is better. We've now submitted a couple of human ratings, and we've recomputed the leaderboard based on these human ratings that we've just submitted. And so if you go back to the leaderboard, you'll see here our GPT-4o Mini has its scores updated, and it has the impact of those human ratings. So we just provided a handful of human ratings, but you can see how they've improved its ELO score because we just voted in favor of GPT-4o Mini in all of those examples. So this is a process that you can use to either do the human evaluation or do the judge or jury style automated evaluation. But you can fully connect this loop here by taking the human ratings that you've submitted via this head-to-head tab and running that fine-tuning process to create your own fine-tuned judge model. If you remember on the slide, fine-tuning can get you 10% or more improvement in accuracy of how your judge model is going to rate which is better. And that 10% improvement, even if the final accuracy score is 70, 75%, that 10% improvement can still really improve the overall rankings in terms of how well they reflect how a human would have voted. So we can do this by coming to the Judges tab and clicking to create a custom fine-tuned judge model. So in this case, we have those couple manual ratings that we just submitted, and we have the 49,000 manual ratings from this LMSys chatbot dataset. And we can say, let's fine tune this Gemma 2 2B model. We can change the system prompt here in this fine tuning job if we want to. And this is estimated for this 2 billion parameter base model. This is estimated to take 5 hours for this fine tuning process. We can go ahead and create that task, which will kick off a batch job that is going to be performing this fine tuning for 3 epochs and uploading the final trained weights to a place where we can then go and run them automatically. And once, so we see here, we have this custom fine tuning task, which is just started. And when this is completed, we'll now have that custom fine-tuned model here, along with some metrics that are saying how accurate it was, because we're holding out some of that data for evaluation. So this process shows you how you can go from a full-featured leaderboard to add a new model and see how it stacks up. But I want to show you as well how it looks to start a new project. So if we deselect that LMSys project, we can go ahead and create a new project here. And I'll just call this new project, create. And we've now created this project. Our next step is to upload our first model results. So I'm going to go click add model, and I can select the GPT-4o Mini CSV that we uploaded, go ahead and upload. And now that we have one model, we have one model in the leaderboard, but it's not ranked yet because it doesn't have any head-to-heads against other models. We can go here and configure an automated judge to create those head-to-heads automatically. I'm going to go ahead and add this same command R model. I'll add the Anthropic Haiku model. If we don't want to be calling any external services, you can run AutoStack locally in your own environment, and you can call any model that's running via OLLAMA. So OLLAMA is great if you want to run LLMs on your regular laptop CPU. You can specify here. Let's say we'll use Gemma 2 9B as a model. And if you just have a CPU, it might be a little bit slower, but you can still use that for rating. And so we've now created this jury with these 3 models, and we can go ahead and add our second model to get those leaderboard rankings. So I'm going to upload results from this Gemma 2 9B model, and we're going to run evaluation using that jury of 3 automated judges that we just configured. So now that we've gone through that process here, you can see if you want to take a look at the head-to-heads between these 2 models, let's go ahead and compare these 2 models head-to-head. And here's, for example, here's how they both answered this function calling question. We can see that we have our automated judging task going, which is being held up by Gemma 2 9B, which is running a little slowly. And we can vote as well as a human. So in this case, explain function calling. I think these are both pretty good, so I'm going to vote tie. And we can go through and provide our human ratings here to improve our leaderboard rankings accordingly. So just with that one human rating here, we see that we have very similar ELO scores. So why don't we provide a couple of more ratings, like random and random. Go to the next. How can I create a test set for a very rare category? I want to build a classifier. let's say that this GPT-4o mini model is better. What is the best way to travel from Tel Aviv to Jerusalem? I think both are good. This one does a better job of modeling how Pikachu would actually talk. And with those couple of human ratings that we've just submitted, we see our leaderboard here stacks GPT-4o mini a little up ahead, but there's still an overlap in those confidence intervals. So until you get those to not overlap, you can't fully trust that GPT-4o mini is actually the better model than this Gemma 2 9B. So our automated head-to-head judging has also now completed. We can see here how this score has evolved over time through all of these automated judgments, as well as our 4 human judgments. And we can see here that, from all of these judges, the trend was generally downward, and the models preferred GPT-4o mini to this Gemma 2 9B model. And again, we can go in here and we can either download those head-to-heads if we want to go process those or poke around ourselves, or we can jump in here and show judging history and see how different models have provided their ratings here. In this case, Claude Haiku is going against the ratings from the other models. In this case, the human is going against the ratings from the other models. And you can use this as a means of kind of understanding the different way that judges have voted in this task. So coming back here to the slides, this AutoStack process gives you faster, less manual, and higher fidelity evaluation that can help you build products faster, help you build better products faster. You'll spend less time on evaluation. So right now, evaluation for many teams looks like manually doing, people call it vibe testing, vibes-based evaluation, where you're looking at some small set of examples and just deciding which one you think is better. This is really good for early stages of projects, but becomes a bottleneck later on when you have many different tweaks that you're making to the system. Maybe you have many different engineers who are working on that same system and doesn't really scale as your product matures. This auto judge process can remove the uncertainty from this vibes-based evaluation. So rather than getting this kind of intuitive read on which one is better, you can get a bit more concrete number on how it ranks against previous versions of your system that you've developed. And this all culminates in helping you build better Gen AI products, having fewer failed POCs, effectively make technical decisions. This could be how to set up your RAG system. This could be which base model to use. This could be your prompt engineering process, and doing a better job at making decisions in each of those stages of putting together a Gen AI app helps you build better products that your users like interacting with more. So finally, if you want to give this a shot, it's currently in private beta, but we're getting ready to open source this product, and we can get you access if you send me an email at gordon@kolena.com. And if you want to run this fine-tuning process here on your own data and see how well the fine-tuned model is at actually ranking for your real domain-specific task, you can start a POC with us, and we'll run through this fine-tuning process and get you some quantified numbers that show how much better and more effective a fine-tuned judge model is at rating for your specific task. Awesome. So I think we have some time for Q&A here. Skip, I'll pass it back to you.
Great. Yeah, we definitely have some questions coming in. Let me go and pull those up. But the first one I see here is just thinking about how many samples are needed to get decent results. You touched on this a little bit, but what would be your recommendation for how many samples you need for decent results?
Yeah, so it depends on the complexity of your task. And I know that this is that kind of wishy-washy answer is not what people are looking for, but it's the reality of the situation. If I go ahead and re-show this slide, it depends on the complexity of your task here, where a simple task is something we've worked with company that is doing something like creating a name for a company based on a description that you might provide to your LLM. Which one is better at generating a unique name that people like, that's memorable, that's not too generic. And this is a very simple task to evaluate. And we found greater than 90% judging accuracy with just 100 or 200, I think it was, samples. So that's an example of a simple task. The most complex task that there is the LMSys task, where LMSys is completely unbounded. users can input anything, the models can output anything, and the user just gets to vote on which is better. So this input could be a request to write code. It could be a request to write a haiku. It could be information about how to travel from one place to another. It could be something adversarial. And so this is about as unbounded as it gets. And in the LMSys task, the data set that they shared is 46,000 examples that can be used for training. And with fine tuning on this, you can get a judge model that's, let's say, 70% accurate, a ceiling of about 70% accuracy for predicting how a human would vote. And a 70% accurate classifier is actually plenty good to generate the actual leaderboard rankings, because as you run many head-to-heads against different models, those that 30% inaccuracy gets smoothed over by having a lot of different head-to-heads and using this ELO ranking system with confidence intervals.
Right. Yeah, on the ELO ranking system, got a couple questions on that in particular. So thinking
Cool.
about how tied votes work in the ELO score calculation,
Yeah,
um, would you recommend adding samples to fine tune there?
definitely. Yeah, I think if you're training something to classify left is better, right is better, or neither is better, including an equal proportion of each of those is kind of the rule of thumb for training a classifier for this judgment process. If tie is a valid outcome for your task, then definitely I would include tie in the fine tuning. If tie is not a valid outcome for your task, I mean, there are some tasks where there is no such thing as a tie. Maybe an American football game never ends in a tie. And the tie is purely optional. If your training data has only A wins or B wins, fine tuning on that will successfully mute out the tie prediction behavior from the judge model, and you'll only get ratings for A or B.
Right. Another question on the ELO. We have somebody asking, is there any way to find trends among a model's history of wins/losses? They say that the chess ELO score approach is great, but not as actionable for improvements.
So for in this case, are we for a model's history? Are we talking about like different prompts that are being fed into that model, or different iterations on the RAG system? If so, without changing your base model, let's say you're always using GPT-4o, these changes to your prompts or changes to your RAG setup would be reflected as different rows, different entries in that leaderboard. We're kind of calling them models here as convenience, but many cases when you're doing, for example, real world development where your base model is fixed, you have an agreement with OpenAI, you are locked into using Gemini models or something like that often happens in the real world. What you would be ranking on this leaderboard is different versions of the system that you're building around that model. So it might be different prompts, different retrieval, different re-ranking systems, different pre and post processing, and much the same way how we see here. Let's go back to this LLMs chatbot arena. Much the same way how we see multiple GPT-4s here, even though they're all GPT-4. Each of these would be a different entry in the leaderboard because it's a different system that behaves differently, whether you're changing the model or the things that are surrounding the model.
Perfect. Question from Raphael here. And
Okay.
this gets a question that I was going to ask too in terms of if this is appropriate for evaluating multimodal AI models. Raphael asks, can I use AutoStack for other models besides LLM? I want to use a jury of LLMs to judge candidates from semantic search.
Interesting. So I think that would fit very cleanly into this setup. I think in this case, your prompt would be the search query that you're using. Let me go ahead and share my screen here. And we'll pick two models so that we're looking at this. So the prompt here would be the search query that you're feeding into your semantic search system. And the response would be the retrieved information, whether that's one chunk or multiple chunks. And the task here of automated judging would be which of these retrieved responses is more relevant to the prompt. And I suspect that we haven't run examples of that, but I suspect that base LLMs would be very good at judging the relevancy of retrieved results. Particularly here, if you come here and add a different system prompt that says, rather than you're a human preference judge tasked with deciding, you update this to say something like, which of these models retrieved a more relevant piece of information based on the user's query. I suspect that would work very well. You can go ahead, create that assistant, and then you can go and see any system prompt that you've changed here. Yeah, I would love to run that experiment. Intuition says it would work very well.
Troy has a follow-up there. He says, similar but separate to Raphael's question, I'm curious how LLM as a judge approaches like RAGAS could be used or could be handled with AutoStack. We're using some open source RAGAS prompts to evaluate the context and the generated text.
So if I understand the RAGAS metrics correctly, you have things like context relevancy and answer sufficiency that are trying to judge these same things. Of how relevant is the retrieved context based on the user's query? How completely does the finally generated answer reflect the content inside the retrieved context? Those are very useful metrics, but I think that they succumb a little bit to the weaknesses that we talked about earlier of trying to make judgments in isolation. If you're looking at just a single model of, okay, here's the retrieved context and here's the response, was this good or not? Is this okay? Is a very hard question to answer. Humans struggle to answer that question and models struggle to answer that question. And so what we found with our own usage of RAGAS questions and with our customers who are using RAGAS as well, that these metrics are good for a directional read, but it can be very challenging to actually use them to make real decisions because they're so noisy. So using this kind of head-to-head comparison where with two versions of a retriever, which retrieved context is better? With two answers generated, which generated answer is better? Which generated answer is more faithful to the retrieved context? I think that you might get rankings that better reflect reality than if you ran those RAGAS metrics on each of those models in isolation and then just ranked those based on that output metric.
Thanks. Yeah. Next question is from Katerina. She says she's curious about prompt engineering. Can you share how AutoStack can be used for prompt engineering? Any automated way to improve prompts? Any work in progress?
So we don't have any automated way to improve prompts yet. I do like that question a lot, and I've personally used the Anthropic prompt engineering copilot to help improve my own prompts. The way that you would evaluate different prompt engineering approaches is by, let's share the screen again. So you try a new prompt, you would then run that against you'd try a new system prompt, you then run that against a couple of different user inputs. We find here that dozens of these is sufficient to get a good read. And so whatever the user inputs are for your domain, you would then go and run that new prompt engineered version on those user inputs, and you would save the outputs from your model with that prompt that you're changing into a CSV here that just has the user prompt and the model response columns. And you would upload this model as like, my model dash prompt 123 or my model dash prompt 324. And then you would see how those different versions of my model, just with the prompt changing, impacts the leaderboard rankings when you upload them and run this automated judging process. We would like to add additional features here to give you a model registry that shows you, let's say with this GPT-4 preview, was there any system prompt, any custom system prompt that we plugged in here? Was there any RAG system? What version of my code base produced this file? We are looking into adding that, but for now, what you would do is just name your models different things corresponding to those different prompts that you're testing out. And you can automate all of this as well. If you have a new prompt, you can automate the process of, okay, now run this on those examples and upload that to AutoStack. And then the judging via one judge or a jury will just take place automatically.
Great. Next question is, How might this work to train on multi-stage conversations?
Go ahead here. I'm going back and forth between screen sharing. So with multi-stage conversations, here you just have the one input prompt and the one output response. But in this input CSV here, you can also include, rather than a single string, you could include a list of user inputs, as well as a list of model outputs. And that'll get parsed as a multi-stage conversation, which just shows you prompt 0, response 0, prompt 1, response 1. And match it up the same way, so that if you have two models here, let's go to one with a shorter. If you have two models here, you would have the first part of that conversation and then the first response, and then the second part of that conversation, and then the second responses from two models, and so on. This is actually the same way that this LMSys chatbot arena dataset is set up, where you have a list of different prompts and responses that correspond to different turns in the chat.
Perfect. All right, we've got just a couple of minutes left. I did want to ask a couple of things. So the first one is AutoStack available to the public? Can people try this out?
It's not quite available yet. We are in the process of making this open source so that you can just download this and run this app locally. If you want to run it now, you can send us a message and we'll get you private beta access where you can try this out for your own flows. It is a single service that you just run locally. Everything that you saw in my demo is running on localhost, and it's built around not sending your data anywhere unless you want to. And so if you want to use if you have fully locked down data and you can't go anywhere, you can use a local judge model from something like Ollama, and just run AutoStack locally, run Ollama locally, and the whole process of judging and ranking these models takes place on the machine. Of course, things like using OpenAI, Cohere, Anthropic judges, those all involve API calls. But you can configure it as well if you have custom endpoints, maybe you use AWS Bedrock or you use Azure AI. You can configure those as judges as well.
Yeah. Quick follow-up here. It says, could this be used for tuning tool calling, ensuring correct tools are called at the right time?
In that case, I think it would work quite well, because function calling is kind of just the LLM returning a special package, specially shaped response. And you would be relying on the judge to know what is the correct tool. But you certainly can set up the judge with a system prompt that gives it an understanding of probably the same tool rundown system prompt that you might already be using, gives it an understanding of what tools you have available, how to call them, when to call them. And then the judge model would be making that judgment of, hey, did this call the right tool in the right place or not? And did it use the right parameters? I think that would work pretty well.
Yeah, makes sense. Last question for you is just thinking about how you developed this. If somebody were thinking about how to implement this kind of automated evaluation system on their own, like how long might that take? What's involved? Yeah, just your perspective on developing this.
I think that if you were to develop this on your own, the tricky part is really just matching this up against previous versions of models, matching all the same prompts, and then running that automated judgment and feeding those automated judgments into the final leaderboard. I think that all of those things are things that you could certainly set up, and in some cases it would be beneficial to just build that into your own infrastructure. But if you want something that's a little bit more full featured and you don't have to write a bunch of different scripts, AutoStack will do that kind of automation process for you once you've configured your judges and started to upload models.
Great. Yeah. Thanks for the insight there. We're pretty much out of time. I see that we do have more questions. I'm sorry we weren't able to get to those, but definitely reach out to email us. Just wanted to show this slide again. If you wanted to give AutoStack a shot, do reach out. We're very happy to have more people getting their hands on this. And some further questions or further resources here. Again, just email Gordon for this. We've got plenty more ML testing evaluation best practices on our blog. It's just kolena.com/blog. If you check out the blog, we also have a metrics glossary if you're looking at that. Any other general questions, comments, feedback on this webinar, please reach out here, skip@kolena.com. And thank you all very much for coming. We will see you next time. Thank you, Gordon.
Thanks, everybody, and thanks for the great questions.